Hello, class. Okay, so we're going to talk about something called Amperes Law, where so far we've been talking about the effects of magnetic fields, and now we want to talk about where magnetic fields come from. And ultimately, magnetic fields come from moving electric charges. We're going to focus on like an actual current. I'll just mention, say we have an atom, where if we look, we can picture an atom, we have a nucleus, and there's an electron, or multiple electrons typically. Let's say that here's hydrogen. So we have an electron orbiting the nucleus. That's actually a current, even though it's just a single charge. This is a current. And so this orbit of the electron kind of creates a magnetic field. Now the nucleus of the atom actually has its own magnetic field as well. And the electron even has an intrinsic magnetic field. So the electron, we kind of consider it just like a point particle. It's probably not really a point particle, it has to have some size. But it's this intrinsic magnetic moment. It's just a property of the electron and has nothing to do with its motion. Ultimately, maybe one day we'll be able to see what's going on inside an electron, but not really there right now. So ultimately, every atom kind of acts like it's a magnet. We've got the nucleus, the electrons both have an intrinsic magnetic moment, or they create a magnetic field intrinsically, and also because of their orbits. So we'll look a little bit about just like, say you have matter on a large scale, it can have magnetic properties which ultimately come down to this atomic level. But we're going to focus more on a larger scale now and just look at currents. So say we have a wire that's carrying a current. And I'm going to draw a standard wire, or just a general picture. Say we have a random wire that's not in any particular shape. And say we wanted to know what magnetic field this wire is going to create. Turns out that's a fairly complicated thing. There is an equation that we could use to describe the magnetic field created by this wire. Kind of like Coulomb's law, where in Coulomb's law, you point charges, you can figure out the electric field due to any individual charge. What we would do for this wire is break it up into pieces. So we could look at like one piece of a wire. And say we wanted the magnetic field at some point P, we could look at this segment of the wire and say, what is a magnetic field at this location P due to this segment of the wire? And it depends on a lot of factors. It depends on the distance from this wire to the point. It would depend on the current and also the direction of the wire. So if like you have a wire in the same location but rotated it, the magnetic field at that point would be different. So just finding the magnetic field due to a single segment of a wire, like a little piece, that if you make it small enough, you can always consider that to be like a straight line segment. That's a fairly complicated thing. And for a random wire like this, you'd have to break it up into little pieces and add up all those pieces. And so there is a way to do that. It's something called the Biot-Savart law. I'll just write down the name here, the Biot-Savart law. Okay, now we are not going to talk about this other than just what I mentioned so far. And even though I'm not even going to write down the equation, the reason I mention it is because I think it's important to understand that we do have a way to calculate the magnetic field due to an arbitrary current. It's just the details of how to actually do that and carrying out those calculations can be complicated. And because we have to break it up into pieces, this pretty much always involves calculus, so we're not going to bother with it. the Biot-Savart law. I just wanted you to know it existed. Just, it is a known solution, how to find the magnetic field due to a wire. Okay, but kind of like we have Coulomb's law, and then we have Gauss's law, which relates the electric flux to the electric field. Or, it relates the charge density to the electric field. And in certain cases, Gauss's law can be used to find electric fields. And there's kind of an equivalent that we can talk about here called Amperes law. And this is actually kind of a complicated thing. So what we're going to do, like in Gauss's law, we had to create a surface. It could be an imaginary surface, and define a flux through it. And for Gauss's law, we had a closed surface. I'll draw it like this. And then, the flux through that surface is proportional to the charge enclosed over epsilon naught. So that's Gauss's law. Amperes law is different. For Amperes law, we actually need an open surface. So I'm going to draw it flat. It doesn't really have to be flat. But just say we have so the surface would be the board just contained in this section here. Now, when I say it doesn't have to be a flat surface, we could have another surface with the same boundary, but maybe it's more of like or we could just make it simpler. We could look at a circle, or you can look at a hemisphere. And as long as they have the same boundary, that's fine. Okay, so for Amperes law, we need an open surface that has a boundary, which is a line. So like here, for a closed surface, the boundary would be a sphere. Here we have an open surface. And let's say there's a magnetic field. I'll just draw some random magnetic field. And let's zoom in on a little portion of our boundary. So we pick a small section of our boundary, and I'm going to redraw this down here. So if it's small, it's basically flat. It has a length we'll call delta L. And the magnetic field in this location is pointing in this direction. So again, that's just zooming in on this little portion of the surface right here. And it'll look like this. And what we want to calculate is the component of the magnetic field that's running along the surface. So we can break the magnetic field into pieces. Let's say we have a piece going in this direction and a piece perpendicular to our line segment. And so I'm going to call this B parallel. That's two parallel lines. That's not B11. And here, the perpendicular. So we draw perpendicular line segments. Okay. So we zoom in on a little portion of the boundary of our surface. And we look at the magnetic field. We break it up into components. So one component is parallel to this line segment. The other is perpendicular. And then what we're going to calculate is B parallel times delta L, which is the length of that line segment. Okay. And we're going to go all the way around our surface. Now, just to be clear, our magnetic field, we have to trace our surface in a particular direction. So let's say we go clockwise. So here, this combination B parallel delta L is going to be 0. If we look at this section here, we're going in this direction, and the magnetic field is, the component of the magnetic field parallel to this line segment. The magnetic field's here. The direction we're tracing and the magnetic field component are pointing in the opposite direction. So if we look at this segment, this B parallel times delta L would be negative. So it can be positive or negative, it depending on, however you trace your curve, if it's going in a particular direction or not. No, if they line up, positive. If they're opposing each other, negative. If they're pointing in opposite directions. And so what we're going to do is we're going to go all the way around this boundary. So again, we have a line that forms a closed curve. That's the boundary of our open surface. Okay, so if we go all the way around this boundary, calculating this for every, along every segment, we add it all up. And what Amperes law is saying is that this is proportional to the current. Now, what current are we talking about? We're talking about a current that passes through this surface. So like here we have a current, say it's coming out of the board. So again, like say this is I1. And over here we have I2. Let's say that one's going into the board, who cares, doesn't matter. Point is, in this case, this B parallel delta L ended up all around the boundary. That would be proportional to I1, because I1 is passing through our surface. Just like in Gauss's law, where we ignored external charges, here we ignore any currents that are not passing through our surface. So, yeah, here we just have, like, say, I1. Say we put an I3 in here, and then it would be proportional to, I1 plus I3. And again, these have directions, like I1's coming out of the board. Let's say this is I3 going into the board. Then we would subtract them because they're pointing in opposite directions. So if we had like 3 amps, and this is 1 amp, then the net current would be 2 amps. And the direction of the current is really given by the right-hand rule. So what we do is we curl our fingers in the direction of this, this loop here clockwise, so our positive direction will be pointing into the board. So in this case, I would actually be like negative 2 amps. If I1 is 3 amps and I3 is 1 amp, yeah, we'd have to call this one positive and this one negative, because of the way we're tracing our circle. So yeah, there is a direction involved as well. Okay, and so I'm gonna erase this picture. Let's go back to this sum here is proportional to the current, where that current is whatever's passing through our surface. Now, to turn this into an equation, we introduce a constant. Let me write it down. I'm going to write it down 2 ways. Okay. So this constant has a name. Oh, yeah, let me write down Amperes law then. With this constant. All right, let me check the units here. Tesla. So here we'd have Tesla meter per amps times amps, Tesla meter. Yeah. Now units check out. So this sum on the left, this kind of this crazy thing on the left, that's proportional to current enclosed. The proportionality constant is called mu naught. It has a name, and I believe it's called the permittivity of free space. So remember, here we have epsilon naught. Which is, so again, these have names. They're the permeability of free space and the permittivity of free space. They're so similar, I always get them confused in my mind. I think this one's called the permittivity, and this one's a permeability. It's possible I'm getting these backwards, though. But usually they're just called mu naught and epsilon naught. Now, why do we put that 0 there? Why not just call them mu and epsilon? In this class, we mainly focus on just like electric fields and magnetic fields. And in general, it's a pretty complicated question. What happens if you have an object, like some piece of matter here, and you apply some kind of field to it, either an electric or a magnetic field? What happens in general is pretty complicated. We talked about dielectrics, how the electric field would be reduced inside this dielectric material. And yeah, similarly, magnetic fields are affected by materials as well. And it depends on a lot of factors, like what type of material. But in some cases, we can use these simple parameters mu and epsilon naught, where the equations are basically the same, except in the presence of matter, instead of having mu naught, you'd have just mu for some material. We don't really get into those details, so no, let's mention it, but then we'll move on. So there's a reason why we call these like the permeability and the permeability of free space. You know, it's just like in a vacuum, which is mostly what we do in this class. But in matter, sometimes we have mu and epsilon that can describe properties of that material. Okay, so that's Amperes Law right here. Now, it's going to raise a question: what good is this? You know, why do we have this? There's two reasons. Well, one, this kind of like Gauss's law. Sometimes we can use Amperes Law to calculate magnetic fields. Another reason Amperes Law is important is because it is one of the fundamental equations of electromagnetism. Just like Newton's laws can describe mechanics, there's a set of equations that describes everything about electromagnetism, like the classical theory. Like what they developed in the 1800s and early 1900s. Eventually, if you study, beyond that, you get into quantum mechanics, which kind of extends the subject, but classical electrodynamics, there are 4 equations, and this is one of the 4. So it's actually, fundamentally, this is an extremely important equation. It looks a little strange in this class. In a calculus-based class, you can give this a little bit more of an elegant form, but yeah, so it just looks a little strange the way we have to write it in this class. But it's a very important equation. I'm going to just do that. So there are a couple cases where we can actually use Amperes Law to calculate magnetic fields. So like for a given current. There's 2 cases we're going to look at. One of those is a long, straight wire. So let's say we have a wire that's coming out of the board. So it's a straight wire coming out of the board, and it's long so we can ignore edge effects, things like that. Now, let's say we surround this wire with compasses. So they've got needles that can rotate and they line up with the magnetic field. What we learn from that is that the magnetic field lines circle around, I'll use red for magnetic field. So these magnetic field lines circle around the wire. So if we have a long straight wire coming out of the board, it would form lines like this, and they have a direction as well, which is given, like everything else in electromagnetism, everything relating magnetism, it's given by the right-hand rule. So if the wire's coming out of the board, you put your thumb out of the board, and your fingers curl in the direction of the magnetic field. So they are circular, and the direction depends on the direction of the current. So if the current was going into the board, then the magnetic field lines would be reversed. They'd be circulating clockwise. Here they're counterclockwise. But again, you can always tell the direction from the right-hand rule. Okay, so what we're going to do is let's pick our surface now. Remember, to use Amperes law, we need some kind of a surface. So what I'm going to do is I'm going to draw a circular surface. Let's say this is our surface. And it's a circle with a radius r. So the boundary of our circle is, the boundary of our circular surface is just a circle. So two really important things happen here. One, let's look at Amperes law. Now, if we were to break, okay, so what we don't know here is the magnetic field. That's what we're trying to find. So if we look at the left side, we have a sum. So we'd have to, let's say we broke this boundary, this circular boundary around our surface. Let's say we broke that into like 20 pieces. What the left side of this would look like is this. So we have 20 pieces. We have a term for each piece that looks like this. And what Amperes law would be telling us, we'd get an equation like this, where B1 would be the magnetic field at the location of line segment 1 that has a length delta L1. And I don't want to clutter up the notation too much. Let's just say, remember, we have to take, if necessary, we break the magnetic field into components and only take the appropriate component. So whatever's going along that line segment. So this is what Amperes law would tell us. And we don't know the magnetic field. So if we break this up into 20 pieces, we have a single equation with 20 unknowns. So again, we're not going to get anywhere with that. We're not going to be able to solve all of this. So in general, Amperes law is not going to just tell you what the magnetic field is. However, in a case like this, there's two very special things that happen here. One, we're kind of taking as an experimental fact that these magnetic field lines are circular. I might actually be able to show you that. I think there's a picture in this book here that it's going to be hard to see. But yeah, this is iron fillings on a sheet of paper. So these iron filings, they kind of line up with the magnetic field. I'll hold this up to the board. I don't know if you'll be able to see it too clearly or not. But this is, I like, being able to see like a real picture. Yeah, you can kind of see, like, they do actually form circles. Particularly see around near the wire. You can actually see like a circle there. So yeah, it is possible to actually take pictures of magnetic fields. The iron filing is one way to do it. So we'll just take it as an experimental fact that this magnetic field line circles around. And we picked our Amperian surface to be a circle. And so in this case, we can say B parallel delta L equals B delta L. So we don't have to worry about breaking things into components. Because any line segment you pick, the magnetic field and that line segment are pointing in the same direction. So we don't have to worry about components. That's one thing. But then we still have this equation. However, because we're dealing with a circular situation here, the magnetic field everywhere on the boundary has to have the same magnitude. Like, how could one point on the circle, like how could, say, this point have a different magnitude than that point? Just from symmetry, that cannot happen. And so what we can say is that B1 equals B2 equals, they're all equal to each other. And so because both of those things happen, we can say that all these B's are the same. we can just call it B. We don't have to distinguish them. So what we have is B times delta L1 plus B times delta L2 and so on. We can factor the B out of this. And again, we'll still say we're breaking this up into 20 pieces. And again, that's proportional to whatever current is passing through it, which in this case is just one wire. Okay. Now we have one more thing remaining. One is this thing in parentheses, delta L1 plus delta L2 plus delta L20. And it turns out this is actually trivial. I can add that up, no problem. This is equal to 2 pi r, the circumference of the circle. So what we did is we broke our circle up, that's the boundary, we broke it up into 20 pieces, and these are just the length of each of those pieces. So if you add up all those pieces, you get the entire length of, the circle, which would be its circumference. That's just obvious. And, yeah, we'll say it's obvious. I only mention that because there's this crazy theorem in math that says if you have a sphere that, say you have a sphere of radius 1, and it's like an infinitesimally thin sphere, just like a two-dimensional surface, there's a theorem that says you can actually break that up into pieces. You can't picture it as an actual physical thing, just a surface, but you can break it up into pieces, and from those pieces you can form two spheres that are each as big as the original one. So it's kind of this crazy theorem. So sometimes you even have to question obvious things, but yeah, in this case, breaking up all these line segments, yeah, safe to say that we just get the circumference of the circle. So ultimately what we have is B times 2 pi r is mu naught I. We don't need Gauss's law anymore. Let's just solve for B. So this is for a long, I'll just say a long wire. It has to be a straight wire, but yeah. Okay. So using Amperes law, we can find the magnetic field due to a wire. Now, using the Biot-Savart law, you could do it as well, but that would actually be a fairly complicated problem. Using Amperes law, it's kind of straightforward. But again, you always want to be careful when using these laws and make sure you actually understand them. Like Gauss's law, you have to know what you're actually calculating. And it can be misleading because, in general, doing these calculations is very complicated. So we only use it in specific cases where the answer is very simple. So you might get the impression that doing this thing on the left side is easy. It's always like the magnetic field times this length or something. But no, don't think it's always that easy. It's just that the rare cases where we can actually calculate magnetic fields from Amperes law, in those cases, this calculation on the left is easy, but in general, it would be extremely difficult. Okay, now I'm going to look at one more example of a magnetic field that we can calculate using Amperes law. And that's something called a solenoid. So first let me draw a solenoid, or try to anyways. I'm not even sure how to draw this. I don't think that should be there. See if that does it. Okay, so basically this is a cross. What the solenoid is, say we take a cylinder like this, and we wrap a single wire around it. So we've got a wire. So let's do it this way. Let's put X's here, and dots here. So what we have is we have this wire that's coming into the board, it wraps around and comes out here, and then it goes in over here. So it just, you have a cylinder, and you literally just wrap a wire around, just wrap a single wire so it carries one current and just all the way down the solenoid. Okay. And we're going to say that the solenoid has a length L. And we want to know what the magnetic field, remember currents create magnetic fields, and here we have a wire, we have a current, and we want to know what the magnetic field would look like due to this solenoid. Actually, I think I have a picture of that as well. Okay, let me hold this up here. So that would be what the magnetic field lines around a solenoid. So like here's our solenoid. It's a cylinder, you're looking down on it. That's what the magnetic field would look like. Now, looks like a fairly complicated picture, but basically, let's say we have a very long solenoid. And when you're in the interior of the solenoid, if you're not near the edges, these magnetic field lines are parallel to each other. When you get near the edges, they spread out, and that complicates matters. So let's say we have a long solenoid. We want to know what the magnetic field is inside. Let's say we can ignore edge effects. So that's, we'll just stay away from the edges. Or say it's so long that the edge effects are insignificant. Okay, now, fairly complicated problem, you might think. We can look at it from this perspective. Say this is the cylinder here, so the wires are wrapping around it. You might wonder, how does the magnetic field depend on where you are inside the cylinder? Let's say we have B1 here and B2 over here. So B1 is right in the center of the cylinder. B2 is kind of close to the wall of the cylinder, or the solenoid. Which one's going to be stronger? There's three possibilities here. B1 equals B2. B1 is greater than B2. Or B1 is less than B2. And the correct answer is that B1 equals B2. So we can actually show this from Amperes Law. What I want to do is I want to draw a loop like this. So let's say here, at the bottom, this is going through the center. We have B1 here, and point B2 is close to the edge of the solenoid. So let's say on that segment, so again, this is a rectangular surface here. And one of these edges is going through the center. The other is parallel to that axis going through the center, but it's close, it's at anywhere except the center. But I drew it so it's kind of close to the solenoid itself. And, let me draw some arrows just to give the direction of the magnetic field lines. And that's determined by the direction of the current using the right-hand rule. Let's see, did I get this? Yeah. So if you look at a wire coming out the top, let's say we have let's just look at one loop. We have a loop here. So the wire is going into the board here, wraps around, it comes out here, forms loops like this. Let's just look at down here. This wire on top, or the right-hand rule, put your thumb in the direction of the current, and so it would create a magnetic field that would loop around like this, going in this direction. And of course, this wire would also create a loop. So yeah, this one is going into the board, so it loops this way. This one's coming out of the board. And so you look in the interior, they're both going to the left. And so, yeah, I totally drew this wrong. Let me fix that. Okay. Yeah, so like they'd both be pointing to the left if you're on the inside. And if you look right between them, they would just add up. Now, if you look over here, like anywhere on this axis, if you look over here, like they might have, like if you look at this point, this one would have a component, we'd have a bigger circle, so it'd have something like this. This one would point in this direction. But if these currents are the same, when you add these up as vectors, it's going to be pointing to the left. And so, yeah, we get these nice straight lines as long as we do not get too close to the edges. And in this case, it would point to the left. So what do I do? We have to pick a direction for this Amperian loop. Let's go clockwise. Doesn't really matter which way we pick. And I'm running out of letters. Let's say the length of this line segment is S. And here, let's call that the height. Yeah, let's call it H and W. Height and width. We have a rectangle. So we want to calculate the magnetic, we want to apply Amperes Law to this situation here. Let me rewrite this. It's often written I enclosed. That's like the current is passing through our surface. Okay, so we can start anywhere on our loop and trace it. Let's start at this point right here. And just go around in the indicated direction. So we go around in a clockwise direction. Okay, so along this segment here, we're tracing to the right and the magnetic field is pointing to the left. And so the result here is we're going to have minus B2 times W. So the negative sign, because we're tracing our loop to the right, but the magnetic field is going to the left. And again, they're parallel to each other, or if you include the directions, they're anti-parallel to each other. And the magnetic field is the same all along, we're considering a very long cylinder. So the magnetic field is going to be the same along that entire width of that rectangle that we're tracing. So we're just going to have B times W. Now, when we look at this segment, we're going to have this B parallel delta L. I'm going to write it down. That's going to be 0. Again, if we look at this line segment, it's in this direction, and the magnetic field is in this direction. There's no B parallel in this case. B parallel is 0. There's no component of that magnetic field in the direction of this line segment, so that is 0. Now we're at this corner, now going across. Now we're tracing our loop in the same direction as the magnetic field. And just like before, the magnetic field is constant along that width of that rectangle. So we have a positive B1 times W. And we have to go all the way around the loop. There's one more piece. And for the same reason this one is 0, this one's going to be 0 as well. They're perpendicular to each other, so there's no, V parallel is 0. Okay, so we add all of that up. And then is equal to mu naught times the current. Now, what is the current in this case? Like, say that there's a wire that loops around this solenoid. Let's say the current in that wire is 10 amps. It's actually a very large current. So then what do we plug in for I? The answer is 0. So let's see if I can think of a physical example here. Looking for a rectangle, basically, a small rectangle. Oh, here. This rectangle is a little bigger. But say this was our Amperian surface. And the I in the equation is what current is passing through this surface. But in the picture, say that our solenoid is bigger and the wire is just looping around. The wire is not crossing the surface at all. There's no current going through the surface. And so what that means is, well, I is 0. So we can factor a W out of here. So we have W times, let's say, B1 minus B2 equals 0, or B1 equals B2, which is, what I kind of told you in advance. But Amperes law can actually show us that that is true. So the magnetic fields, if you're right in the center, again, like say here's your solenoid, magnetic field right in the center would be, you can move, let's say you had a probe that could measure the magnetic field. So you put your probe in here, move it around, you're going to register the same thing. Magnetic field doesn't matter where you are inside the solenoid, as long as you're deep in the solenoid and not near the edges. Okay, but now we want to know what the magnetic field actually is. Oh, one more thing, the magnetic field outside the solenoid is 0. Now, it might not look like that from the picture I showed you. And the reason why it doesn't look like that is because for a real solenoid, the magnetic field outside is not going to be perfectly 0. However, if we had an infinitely long solenoid, then the magnetic field outside would be 0. You'd have a constant magnetic field inside, nothing outside. And for a real solenoid, it is a finite length, but basically the magnetic field outside the solenoid, we can't really say it's 0, but it is very small. So now let's focus on finding the magnetic field inside the solenoid. So let's erase that. I'm going to draw a different Amperian loop here. So we have a rectangle like before, but now our solenoid is, cutting through this rectangle. Now, we've got X's here. Remember the right-hand rule. If you put your thumb in the direction of the current, the right-hand rule gives us a direction. So let's say our direction that we're going to trace our loop. It'll be a little easier if we just go clockwise in this case. So let's do this. We're going to apply Amperes law. And again, I drew this little, askew, but like this, these are parallel inside. So like the lines of these rectangles are all either parallel to the axis of the solenoid or perpendicular to it. Okay, so let's apply Amperes law here. Yeah, we can get rid of that as well. Okay, so we've got to go around our loop. Let's do what we did before. Let's start here. And let's go along this line segment from here to here. Now remember I said the magnetic field outside of the solenoid is essentially 0, well, if that's 0, this B parallel delta L is going to be 0. So that first segment, we have 0. And then our second segment is also going to be 0. Now, to do this with Amperes law, we'd have to break it up into two pieces. Like, one piece is outside of the solenoid, where the magnetic field is 0, so B parallel delta L over this piece is going to be 0. We might have something inside, because we do have a magnetic field inside, but just like before, the magnetic field is perpendicular to this line segment, so we get zeros for both of these pieces, both inside and outside the solenoid, but we get 0 for different reasons. So I just wanted to mention that. So it's 0 again. So now we're going along this segment. And again, we have a constant magnetic field here. It's the same at every point along this segment because we have a very long solenoid. So if you're far from the edges, it doesn't really matter where you are on this line segment. The magnetic field is the same. And so what we're going to get for this segment is just B times L. So we're a magnetic field and that line segment. They're both oriented the same way. They're both going to the left. And then this last piece is 0 as well. For the same reason, that piece is 0. Okay, now that's equal to what? Well, we've got our constant. And now we want the current here. The current that's passing through the surface. Now, there's a current I, let's say this wire, let's say the wire comes in here, and so we have a wire going in, it loops around a bunch of times, and it comes out here. So the current is I. However, we want the current that's passing through the surface. And, just from the picture, it's like we have I here, and here, and here, and here. We can say N times I. So I is the current in the wire, but N is the number of times our wire crossed this surface. Because it keeps looping around, so it's going to go through the surface multiple times. So N is the number of times that we cross our surface. Okay. So now let's solve this. B is equal to mu naught Ni over L. Let's call this W like before. Okay. I'll change that later, but for now, we'll call this W because that's the length of that line segment of our Amperian loop. Okay, now, when you look at this result, you want to be a little bit cautious. Remember, we have an actual solenoid, and we want to know the magnetic field inside, and what we get here, it depends on W, where W is the width of this Amperian loop that we just made up. So this Amperian loop doesn't really exist. We could have just as well picked a smaller rectangle. So what if W was smaller? Would that make the magnetic field bigger? If you lower the denominator, that makes the fraction overall larger. The thing is, what if we cut W in half? So what we'd have in that case, we'd replace W with W over 2. However, if we cut our loop in half, we'd only have half as many crossings. Our wire would only cross half as many times. So on top, we'd have an N over 2 would be the number of crossings. And so these 2's cancel out. And so we get the exact same result. So it kind of looks like our result depends on W, but it doesn't really. W can be anything and we're going to get the exact same answer. Okay. So, important to point that out. Now, what we usually do, as far as defining things, let's say capital N is the number of turns. So if you have a solenoid, if you take a wire and wrap it around 100 times, capital N would be 100. L is the length of the cylinder. Or I'll just say the length of the solenoid. And we're going to define little n to be the turn density. So what we have, I'm going to actually write that down here. Little n would be big N over L. So usually this would be like some number per centimeter. I mean, you could have number like per meter, but that'd be a pretty big solenoid if you had it measured in meters. So you might have something like this solenoid has 80 turns per centimeter. So like if you just look at a 1-inch segment, the loop would wrap around 80 times. Okay. Now, let's extend this loop to be the entire length of the solenoid. In that case, W would equal L. Now, there's a little bit of an issue here because we've been assuming that the magnetic field was the same everywhere, which is true until you get close to the edges. So this is a little bit of an approximation. We're ignoring edge effects. But again, it's not a problem. This gives us a very realistic result for the magnetic field. And this big N over L is the turns ratio. Yeah, I think it's called the turns ratio, not density. Whatever you want to call it. So we can say for our solenoid, we get this nice simple expression. B is equal to mu naught little n times I. So this would be, the turns ratio. That'd be typically like number of turns per centimeter would probably be the units that we would use. Okay, so I think that'll be it for now. I want to record in a separate lecture though. I want to actually calculate the magnetic field inside a solenoid, but I want to keep the length somewhat reasonable. That problem won't take too long, but I think it makes more sense just to have, like if I do example problems, I'll try to do those in separate videos, just so, it might be easier just to watch it that way as well. So anyways, this will be it for this video, but then we'll do an actual example with calculating the magnetic field of a solenoid. All right.